A statistics professor was describing sampling theory to his class, explaining how a sample can be studied and used to generalize a population. One of the students in the back of the room kept shaking his head. "What's the matter?" asked the professor. "I don't believe it," said the student. "Why not study the whole population in the first place?" The professor continued explaining the ideas of random and representative samples. The student still shook his head. The professor launched into the mechanics of proportional stratified samples, randomized cluster sampling, the standard error of the mean, and the central limit theorem. The student remained unconvinced, saying, "Too much theory, too risky. I can't trust just a few numbers in place of all of them." Attempting a more practical example, the professor then explained the scientific rigor and meticulous sample selection of the Nielsen television ratings, which are used to determine how multiple millions of advertising dollars are spent. The student remained unimpressed, saying, "You mean that just a sample of a few thousand can tell us exactly what over 250 million people are doing?" Finally, the professor, somewhat disgruntled with the skepticism, replied, "Well, the next time you go to the campus clinic and they want to do a blood test, tell them that's not good enough. Tell them to take it all." Which is why we don't always want to do a census. Anyways, going back to performing a study and the different types of studies. You are tasked with determining if listening to classical music improves grades. You decide to interview some friends for your study. What variables could you record in your survey? Well, we could record what was your last grade. Do you listen to classical music while you study for your last test? And by the way, this one's quantitative and numerical. This one's categorical, yes or no. Or do you listen to classical music? They went in reverse order, but that's okay. All right, so there's several forms of studies. What could be the population of this study? I'll answer that in a sec. We perform a census when we collect data from every individual in the population. So that's if they take all your blood and measure it. So that would be a census. And you can see why we wouldn't always want to do that. Sometimes we just want to take a little bit of your blood, which is better, and that's called a sampling. So where we do it from a few individuals from the population. In our case, where we're looking at the music, the population would be the students. Now, you might actually prefer to collect data, actual data from observations instead of just doing a survey of your friends in classical music. You might actually want to watch and see what music they listen to and then record the results. So in an observational study, we let the subjects choose. So I wouldn't make one student choose country music and another one choose classical. They get to choose. Then we observe them and record the results. Now, observational studies do not change the variable being recorded, so we're just recording what happens. While observational studies have the advantage that we can record the data and determine if there is an association, it does not imply causation. So, why might that be? Because there might be a lurking variable, basically. For example, people who listen to classical music, if you think of people who listen to classical music, they tend to be more hoity-toity. They tend to be more educated. Well, if they're more educated, they tend to put a bigger focus on education, and that might lead to their kids listening to classical music and an emphasis on good grades there. So there could be a lurking variable that is explaining it. It may not be classical music that is causing the good grades. It could be that the environment is causing both classical music and the good grades. Now, if you really want to determine causation, then what you really need to do is randomly assign subjects to different treatment groups. This is called an experiment. You then record and analyze the results. First of all, this is a typical diagram for an experiment. You're going to have subjects. They go into the hat. They're randomly assigned to different groups. Here I just have two groups, group 1 and group 2. And each group is going to receive a different treatment. So we impose a treatment on the group. We have a control group to ideally create a baseline, and we keep other variables the same for all groups. One thing that's important is we create groups from subjects to distinguish results from chance. So that's the whole point here, is we're creating replication to account for that. Then we're going to compare the response variable. So let's go ahead and talk about some of these terms. The experimental unit is the smallest collection of individuals to which a treatment can be applied. So usually these are known as the subjects. The factor is the explanatory variable. In other words, what's causing the difference. The treatment is whatever we're applying. Now, there can be different treatments using the same factors, and I'll go over that in some examples. Now, if there are different dosages of the treatment, then these are known as the levels. Typically, the factor is associated with the treatment. So usually, like in one example, we're going to talk about fertilizers, and there are 3 different types. So there are 3 levels, and the factor is the type of fertilizer. So ideally, experiments should have a control group. This purpose is to provide a baseline so you can compare what is normal to what you're getting from the treatment. Sometimes subjects are assigned a fake treatment. The reason is if you have a control group and they know other people are getting pills, they're going to feel not as, well, actually, it's the other people getting pills that's the problem. They're going to take the pill, and even if it's a sugar pill, they may think they're doing better. In fact, placebos are like the most effective treatment out there. They help everybody because of something called the placebo effect, which is primarily psychological. They say, ooh, I took a pill, I feel better. Kind of like when your mom kissed your boo-boos. You're like, oh, it still hurts, but you feel better because mom kissed it. All right. So by randomizing and using placebos, when possible, we can control for the impact of lurking or confounding variables. On the AP test, we primarily use the term confounding variables. You don't tend to see the word lurking anymore. I guess it was too, I don't know, sinister. Blinding prevents bias by hiding the treatment type from the observer and or the subjects. And if you blind one side, it is single blind. If you blind both sides, it's double blind. And so the reason we might blind the subjects is we don't want them to have some sort of psychological, oh, I feel better. And there's also a good reason to blind the observers. In some senses, for example, if a teacher thinks that a student has a higher IQ, they actually tend to grade them higher without meaning to. They tend to also motivate them more, and they tend to teach them more. So as a teacher, we try to blind ourselves and treat all of you equally, and so that we don't have a disparity in how we teach among you. Double blind is when neither the observer or the subject can see the treatment type. One of my favorite examples of a double blind is on Grey's Anatomy. They had this treatment, I think it was for cancer. And the doctors would assign they would give the treatment, but they didn't know which one they were giving to the patient. And the subjects also didn't know which one they were giving. So they actually one of the doctors broke in and she switched it because she wanted to make sure her subject was getting the treatment because she was hoping it would help her subject. Okay, now a key principle of random assignment, and we're going to go into this in the next lesson in more detail, but all subjects must have an equal opportunity to be assigned to any of the treatment groups. The purpose of randomization is to create comparable groups. So if your method of assignment kind of prefers the people in front or a certain group, they're not going to be as comparable. So where the effects of confounding variables should be roughly the same. Now, confounding occurs when 2 variables are associated in such a way that they're affecting the response, and you can't tell if it's a treatment causing the response or this other variable. So to validate the results of an experiment, it is always important to replicate the experiment to see if they are repeatable. Here's an excellent example. So this is true. In 1992, there were several observational studies of women who took hormones and those who didn't. And they noticed that women who took hormones had less heart attacks than women who didn't take hormones. But then in 2002, they did several experiments to say, hey, okay, this hormone thing, is it helping? And they found out, no, it actually has no impact whatsoever. So first of all, what is the difference between the 1992 studies and the 2002 studies? Well, the first one in 1992 was an observation. It tells you here, observational study, right there. The other study was an experiment. Well, how can we tell so what does that mean? How are they different? Well, in an observation, subjects choose. They don't get to choose in experiments. So what was the confounding variable and why did it influence these studies of 1992? Well, think about it. A woman who has to go see a doctor if she's going to take hormones. Women who don't see doctors are probably less health conscious and more likely to get a heart attack than women who don't. All right. In fact, I was just at the doctor today because I see my doctor regularly. All right. Two more examples. We have a farm product manufacturer wants to determine if the yield of a crop is different when the soil is treated with 3 different types of fertilizers. 15 similar plots of land are planted with the same type of seed, but are fertilized differently. At the end of the growing season, the mean yield from the sample plots is compared. So what are the experimental units? I'm just going to say the plots of land right now. Those are your different subjects. The factor, well, it's going to be the type of fertilizer. How many levels? Well, we have 3 types of fertilizers, so we have 3 treatment groups in that. What is the response variable? We're trying to measure the mean yield. All right, so if that's better, we're going to guess the fertilizer is better. How many treatments? Well, I only pretty much have 3 types of fertilizer, so that's how many treatments we have. Now, why do we use the same type of seed on all 15 plots? Well, we want to make sure that we're trying to minimize confounding variables. So different types of seeds may have different types of yields. So we're trying to control for the type of seed. Last example. A consumer group wants to test cake pans to see which works the best, bakes evenly. It will test aluminum, glass, and plastic pans in both gas and electric ovens. So what are the experimental units? Well, the thing I'm going to be looking at are actual cakes. All right, so I'm going to take a look at them. The factor is, well, there's 2 really, the types of pan and the type of oven. All right, how many levels? Well, we have 2 different ovens and 3 different types of pans. So we have 2 for one, 3 for the other. What is the response variable? Well, we're going to check which one bakes evenly. So the evenness of baking is the response variable. How many treatment groups will I need? Well, I'm going to need 3 pans in one oven and 3 pans in the other. So I will need 6 treatments. A key principle of random assignment for experiments is that all subjects must have an equal opportunity to be assigned to any of the treatment groups. So how do we do random assignment? Well, first of all, I'm going to show you this example where they're examining 2 curriculums, well, the normal plus something called Career Start. And this is one experimental design. Now, on the AP test, don't just draw a diagram. You have to explain how the treatments are assigned and what will be measured and compared. So it may seem like you're kind of showing it here, but you have to provide more detail. So describe how you would randomly assign 14 middle schools to each of the 2 methods. And we're going to talk about the hat method, using technology, and using a random number table. So, but before I do that, let's talk about this experiment. What are the experimental units? The middle schools. The factor is Career Start. We think that's going to create a difference. The explanatory variable is the curriculum type. Very often these 2 are very much related, the factor and the explanatory variable. The treatments, well, we're going to get normal curriculum or normal curriculum and Career Start, so that would be the levels. And the response variables are all these. We're going to compare attendance, behavior, test scores, engagement, and graduation rates. So if I was going to assign the 14 middle schools using the hat method, which is always the simplest, the gold standard, well, write each name, subject's name on one of the slips, in this case, one of the school names. Put all the slips in the hat and mix thoroughly. Draw them out one at a time until you have 7 slips. Everyone had a shot at being in the first group, and that's good. So those 7 slips will get the treatment of the normal curriculum and Career Start, and the remaining will just get the normal curriculum. An alternative, which works fine as well, is write Career Start on 7 slips and regular curriculum on 7 slips. Put them in a hat, mix it thoroughly, have the subjects come up one by one and pick up a slip from the hat. This guarantees that 7 schools per group with the treatments are assigned by chance. And as you recall, we looked at that 2018 AP question or actually 2017 free response question, where they did the chip method and the flipping the coin method, and this is a lot like the chip method in that example. So using technology, give numbers 1 to 14 to the schools in alphabetical order, and then we use a random integer function, which is under math, PRV, and generate random numbers. So you can say, give me random numbers from 1 through 14. Make sure to ignore any repeated numbers. It's not like a school's going to participate twice. And once the first 7 different numbers are chosen, those are the ones in the first treatment group. And the second group, the rest go in the second treatment group. Finally, a random number table. With this one, it's a little difficult because if I do 1 through 14 and use 2 digits, it's going to take a while. So what I'm going to do is actually divide the digits from 0 to 99 among the 14 schools equally. A little unorthodox, but it'll work. So I'm going to say 0, 0 to 06 is school 1, and I'm going to go in groups of 7 all the way until I get to school 14, which will be getting up to 97, and ignore 98 and 99 because I don't want any school to have a more than equal chance than the others. I'm going to use a line on the random number table, select 2-digit numbers for each school, ignoring repeats till you have selected 7 unique schools for the treatment. So here's my random number line, and so I'm going to read it in 2-digit groups, moving from left to right. So the first 14 labels identify the 17 schools assigned to treatment 1. Actually, it should be first 7. All right, so this first group, that would be group 3. So if I go 00 to 06, then 07 to 013, this would be in the 3rd group. This one would be in the 6th group, and this one would be in the 13th group. So far I have 3 different schools, school 3, school 6, school 13. Then 18 I'm not going to use because that's actually in group 3, and I already pulled that one. 99 is one of my ignores. 04 is group 1. 15 would be in group 3 again. 35 would be in group 6. 33 would be in group 5. 81 is in group 12. 79 is also in group 12. 40, we already pulled 40. 12 is in group 2, which means I'm, let's see, I'm almost there. I've got 1, 2, 3, 4, 5, 6. 14 is in group 3, believe it or not. 38, I've already used. 83, no, that's group 1. 59 is group 9. So the schools I would choose are schools 1, 3, 6, 1, 2, 3, 6, 1, 2, 3, 5, 6, 9, 12, and 13 if I'm trying to go in order. So it's a little more difficult using the random number table rather than, say, technology or the simplest, which is the HAP method. So what if I just flip a coin? And I'm going to go ahead and go over this again. We sort of covered this. We did cover this with the 2017 free response question number 6. But a lot of times people think, if you just flip a coin as you go through, that would be fine. And it is, as long as all subjects toss a coin and it's still completely randomized design. If you're only tossing until you fill the group, that's where the problem comes in. All right? So usually we want the groups to be equal. So what happens if we force the groups to be equal? We keep flipping until one of the treatments is filled. Once it's filled, then every other subject on the list is forced into the other group. They are no longer assigned by chance. And the last subjects on the list will almost always be assigned to the unfilled group, leading to a bias. What if we had the schools listed by the time they signed up when the first schools be a little more enthusiastic? So that might be a source of bias. So this is a problem. We should not force the groups to be equal. We should use one of the other methods. But just in case you didn't get it, and this was for my prior year when I didn't cover that example, we have Amy, Bettina, Carl, and David, and we want to put them in 2 groups, and we're going to have them flip heads or tails. Heads is group A, tails is group B. So the probability of heads and heads is 1/4. Tails and tails is 1/4. Heads, tails, heads is 1/8. So I'm just flipping until I have a group filled. And we kind of worked through that on our example. So the probability that Amy and Bettina are in group A by flipping a coin is 1/4. Now there are 6 possible different outcomes, but 16 ways to flip the coins. We're basically ignoring 10 invalid outcomes because our groups would be filled. So you can see here, these are the outcomes that fit that. Well, there's 6 different groups, so the probability should be 1/6 for each. The hat method will work, but the coin flipping method will not. Now, last but not least on this part of the notes, I did an experiment to compare automated grading to grading by hand for classwork and to see if it could improve my students' mastery. So how could we create a completely randomized design? Well, I would take my students' names, put them in a hat, split them between group 1 and group 2. So I would draw students until group 1 is filled and the rest go to group 2. And I do automated grading on group 1, regular grading on group 2, and use their DCA scores as a response variable. So this was for my geometry group that I compared scores on. Besides completely randomized design, there are 2 other variations on experimental design, including blocked and matched pairs. So why do we pursue these? The main reason we might is if we can't control all the factors that might affect the outcomes. There are certain things we cannot assign to subjects. We can't tell them their sex, their ethnicity, their age, the day of the week, if we're looking at production, batch, or size. All of those might have some differences compared to others that we want to control for. So our solution is to run separate experiments based on the factors you can't control. So a blocked experiment basically looks like 2 regular experiments. You have your block 1 subjects, group 1, group 2, or more if you need, treatment 1 and treatment 2, and then you compare. Then you have your second block, group 3, group 4, they both get the treatments and you compare. So you basically have 2 or more experiments where you block them according to ethnicity or gender or age because of they're going to respond differently because of those factors. So let's go ahead and create a completely randomized block design for my investigation of grading, automated grading. So if I had pre-AP geometry, that would be one group that I would block for. And if I had regular geometry, I would block for them separately because there would be a lot of difference in these 2 scores based on the way the classes are. So I wouldn't want to have my pre-AP geometry mixed with my regular geometry. Now, sometimes the variability in the blocks is still too big and it masks the effects of a treatment. In this instance, you want to more closely match subjects or trials based on similar factors. So here you have your pairs. You're going to pair them up. Frequently, twins is a common type of pair, or you could have husband-wives, depending on what's going on. All right. Match pairs is great when you have either matching pairs of experimental units, such as twins, and then you randomize the treatment in the block. Or you can apply 2 different treatments to each unit. This is actually very common. And it could be before and after, pre-test and post-test, or no randomization at all. Now, I actually did use a match pairs for my initial investigation. Why did I do that? Well, first of all, let's see how I use match pairs. Basically, I graded all my students using regular grading in the fall. And then I graded the same students using automated grading in the spring. So this was sort of a before and after, and I was comparing them to district scores to see if they improved. And they did, by the way. So why did I use matched pairs instead of one of the other designs? Because you could say, well, you know, maybe something changed from spring to fall, actually, or fall to spring. And actually, it's harder in the spring. So if anything, the score should have gone down, not up. Why did I use match pairs? Well, it would be very hard for me to have 2 grading systems going on in the same course, and especially in the same classroom. It wouldn't be fair to the students for me to grade one student one way and one student the other way, especially if the grading actually provided an advantage to one of the groups. When I do version quizzes and tests, I try very much to keep them equal. For the same reason, I want to make sure my students have fair assessments across the board. Now, do be careful. Make sure nothing else changes on a before or after. So if I had changed my curriculum or my note style or anything else that was a big factor, that would affect my results. Bad things can happen to good experiments, so record any data that may be relevant. It's always good to pre-test surveys and experiments.